All right, everybody, we're going to be talking about data analysis. We're going to be talking about this for a while. This is going to be part one of this lecture. Um, so, statistics allow us to evaluate relations between variables. Is one thing related to another thing? Is one thing different from another thing? And if yes, how different is it from the other? And we'll be talking a lot today about different types of data and then how to present that data, just the sort of the raw data, the raw numbers. Data refers to any type of information collected for use in research or assessment. It can be numerical, verbal, or graphic. We're going to be talking about the numerical data today. So we're going to be talking about quantitative data. Really, for most of the rest of the course, we'll be talking about quantitative numerical data. There are four levels of variables that could be measured quantitatively. And these are going to be really important for you to know. They're going to be a big part of your final exam because number one, you've got to know what kind of level your data is, whether it's nominal, ordinal, interval, or ratio. And once you know what scale or level it is, that's going to tell you how you can analyze that data. So this is going to be, again, a big chunk of your final exam right here. All right, nominal scales or nominal data. These are variables that are categorical and represent discretely separate groups or categories. Think naming, that's what the nominal means. So we're going to look at things that are like correct, incorrect, whether somebody is fluent or a person who stutters, whether someone's a Democrat or a Republican. And what's important to know about this data is there's no average score and you cannot multiply or divide. So what do we mean? All right, so let's say we took we wanted to see, is there a difference in whether students are Democrats or Republicans based upon their major? And we wanted to compare people in social work versus people majoring in economics. And we were going to count up the number of Democrats and Republicans. And we find that in social work, let's say there are 20 students, there are 17 Democrats and 3 Republicans. I'm just making that up. And so that's our data. So what's the average number of people in that class who are Democrats? Well, there actually is no average. The number is 17. That's just each person counts as one, and each person either goes into the Democratic category or the Republican category. And there's no average. And you can't multiply or divide, right? It's just you're either a Democrat or you're a Republican. We're going to make people like we're going to force them to choose, and that's it. There's no, so it kind of isn't real numbers because we can't average, we can't multiply or divide. And if we were doing a study to see, for preschoolers who stutter, about 75% of them are going to become normally fluent speakers within about 3 years of onset. So if we wanted to do a study and we took, we took 30 preschoolers who stuttered and when they were 3, and we tracked them and we assessed them again when they're 7, and let's say 25 of them were fluent speakers when they're 7 and 5 of them are children who stutter. What's the average? Well, there is no average. It's just 25 and 5. You can't multiply, you can't divide. Each person counts as one, and each person goes into one category. So these are just sort of it's a categorical variable. So again, It's a little bit different from other, and it'll make more sense as we talk about the other scales. Now we've got ordinal scales. These are categories in rank order, high to low, low to high. Information is ranked, but it cannot be multiplied or divided. So here, think about a voice rating scale, an attitudinal scale, teacher evaluations, Olympic medals, right? Whether you're going 1 to 7, 1 to 3, right? Olympic medals, gold, silver, and bronze is kind of like 1 to 3. So if we had everybody rate their voice on a scale of 1 to 7, where 1 is pleasant and 7 is unpleasant, right? So each person would put down, or we could rate other people's voices or whatever. You put down a 2 for one person and a 4 for another person. So here again, are these real numbers is kind of what we're looking at. And the reason they're not is a couple reasons. Number one, right, we could really substitute, instead of 1, 2, 3, 4, 5, 6, 7, we could substitute A, B, C, D, E, F, G, right? It'd be the same thing. Because we can't multiply and divide, right? Let's say you listen to one person and you give them a 2 for pleasantness, and then you rate somebody else and give them a 4. Well, is that second person who you give a 4, is their voice exactly half as unpleasant as a 2? No, right? You said, this person's kind of in the middle. They're not really pleasant. They're not unpleasant. I'm going to give them a 4. The first person, I really liked listening to their voice. It's not the greatest ever, but it's nice. So I give them a 2, right? So you can't multiply, you can't divide. You can't say the person who had a 2 was twice as pleasant as a 4, right? So again, we kind of don't have real numbers. So nominal and ordinal scales are going to be treated in a different way. When we go, later on, when we go and talk about how we're going to do inferential statistics and decide whether there's a difference or not a difference, we're going to have to treat these really differently because they're not treated as real numbers. You can't multiply or divide, and you can't really get an average score. Certainly in nominal, there's no average score. And even in ordinal, you can argue that there's no average score either, because again, a 4 isn't really twice as good or twice as bad as a 2. It's just lower or higher. So, nominal and ordinal data are not going to be treated as being real numbers. All right, so let's talk about the 2 scales or levels of data that we can treat as real numbers. The first is interval scales. Interval scales categorize and rank data, and the distance between the scores is equal, right? There's no true 0 point. I'll talk about that in a second. And there's an arbitrary maximum point. The best, most common example of an interval scale is a test score, right? So the distance between the scores is equal. If you get an 80 and your friend gets a 40 on the midterm, right, your score was twice what your friend's score was, right? Your score was 2 times what their score was. So the difference between the scores is equal. You can multiply, you can divide. However, so we can treat this as real numbers, but they're not the realest of numbers. So number one, there's no true 0 point. A true 0 point means that if you got a 0, that it doesn't actually exist, right? So if if we've got people running a 5K and one person's time for running the 5K was 0.0, that means they never actually ran the race. The race never happened for that person. It didn't exist. However, If you get a 0 on the midterm, does that grade exist? Yes, right? That 0 is as much of a score as a 40, as an 80, as a 100. It's just the first point on the continuum. So, right, a test score doesn't have a true 0 point. A 0 is just another grade. Whereas if somebody's height is 0.0, they have no height. There is no height, right? So that's what we're talking about with a true 0. And then there's an arbitrary maximum point, right? On a test, the highest you can get is 100, or if there's extra credit, the highest you can get is 104, right? But there's an arbitrary maximum point that you can get. So that would be interval data. If you can multiply the data, you can divide, you can get an average score. However, there's no true 0 point, and there's an arbitrary maximum point. That then is interval data. All right. Our final level of measurement is what we're going to refer to as true numbers. And these are ratio scales, ratio levels. These are variables that have a true 0 point and no arbitrarily set limit, right? So if we were going to look at time, right, the time to complete a race, let's say we were going to say, how long will it take somebody to run from Wilmington, North Carolina to Los Angeles, right? It could take an infinite number of time, right? There's no arbitrarily set limit. They could take a year, they could take a month, I don't know. And then also, are we going to measure them in seconds? Are we going to measure them in tenths of seconds, hundreds of seconds, thousands of seconds? So not only is there no limit on how long the race could take, but there's also no limit on how we could measure the timing of it. So there's no arbitrarily set limit, and there's a true 0 point. If it took somebody 0.0 seconds to go from Wilmington to Los Angeles, that means they never showed up. They never raced. The race never happened, right? And the same thing is true for height, for weight, right? If someone's weight is 0.000, they have no weight. That person doesn't exist, right? So we've got a true 0 point and no arbitrarily set limit. So interval and ratio data are going to be treated as real numbers. You can multiply, divide, get a mean, a median, a mode, and at least in theory, they're going to have a bell curve, right? And we'll talk about a bell curve a little bit later, and then certainly in the next lecture as well, right, where there's going to be curve. Most people are going to be in the middle, and then less people are going to be, right, really low, and less people are going to be really high. Right, so that's that. So interval and ratio data we can treat as real numbers, whereas nominal and ordinal data we're going to treat as sort of pseudo numbers. All right, and again, this will make more sense too when we talk about how we're going to analyze data, but that comes later. All right, so we've got our numbers, we've got our stats. So let's talk about descriptive statistics. These are going to be used to summarize data using either graphical or mathematical procedures. And with descriptive stats, we're really just going to summarize performance, okay? So you can put it in a table. So these are scores on parts of a test. We've got the pre-test average score and the standard deviation, and the post-test average score. So people improved in knowledge, in skills, skill 1, skill 2, skill 3, and skill 4, all improved. All right. These, the average, the mean, and the standard deviation are going to be descriptive statistics, right? The p-value and the Cohen's d are going to be inferential statistics, which we'll talk about later. But when we're just talking about descriptive, right, here's their score, here's the average score, here's the standard deviation, just here are the raw numbers, here's the data, right? And again, these are test scores, so what type of data is it? Is it nominal? Is it ordinal? Is it interval or ratio? Remember, test scores are going to be interval data. Okay. Now, so that was listing out using numbers to talk about the data, but you can also do it graphically, right? Where we can display each score and the frequency that it occurred in a table or a graph. The horizontal axis going across is going to be the x-axis, and the vertical axis going up and down is going to be the y-axis. And these allow us to look for outlier scores, right? Scores that are really different from the rest. So do we have a cluster of scores and then one or two that maybe don't make sense or are totally different? So it's going to help us be able to see visually our data, right? So there are a couple ways to do that. We've got normal distribution, which is going to be that bell-shaped curve, symmetrical curve. It's the most frequent scores are going to be clustered in the middle, right? So, and we're going to spend a lot of time in the next lecture looking at a bell curve at that normal distribution, right? Most scores are going to be in the middle, right? The exact middle is the mode, the median, and the mean are going to be right in the middle. It's going to be the most common score is also going to be the average score is going to be the score in the middle, right? So, and we'll talk more about this later, right? So it's a nice normal distribution of data. However, usually to get a nice, perfect curve like that, they do some stats with that and they change it up a little bit. A lot of data is going to be either negatively skewed or positively skewed. So a negatively skewed distribution is where most scores are high, but some scores are low, right? So if you think about grades in a lot of our CSD classes, right, most people get an A or a B, and then some scores skew negatively. So most scores are high, but some scores skew negatively. That's a negatively skewed distribution. Right. A positively skewed distribution is the opposite. This is where most scores are low, but some skew high, right? So have you ever taken like a chemistry class, a really hard science class, and there's a teacher that's just really difficult and it's just really hard, and the average score is like a 60. Most scores are low, but there are a couple people that get, one person gets a B, one person gets an A, right? So most scores are low, but some skew high, right? So here's that negative skew. This would be like grades in our CSD classes, right? Most scores are high, but some grades skew negatively, right? This is a positively skewed course where most grades are low, right? But some skew positively. So it might be a little bit different from what you'd think from the very beginning, right? So positively skewed, most scores are low, but some skew positively. Okay. And you can also have a bimodal distribution where you've got two clusters of scores, right? So here, right, you could have a course where you've got grad students, it's broken up, and you've got some grad students in the course and some undergrad students in the course, right? So maybe the grad students all get A's in the course, but it's a really hard course. So there are almost no B's and some C's, and a lot of the undergraduates, the average grade is like a D for the undergrads. So undergrads are here, and then grad students are here, right? So that would be a bimodal distribution where we've got two clusters of scores. And then we're going to actually wait for measures of central tendency for next time, and we're going to stop right here.